Okay, Valeria, if you'd like to introduce the session, please.
Yes. So hello to everyone. Join us this morning. I'm Valeria Korol and I'll be chairing this plenary session for you. And this morning I'm joined by Gillian, Victoria, Nikos and Martina. So we will hear some updates about the James Webb. Then we will be back on Earth, talk about astronomers and the climate crisis, after which we will take a short pause and we come back to talk about stochastic gravitational wave signals with LISA, and we will conclude this plenary session with the talk about LISA early career scientists. So before we start, let me remind you a few details. So we will take all questions at the end of each presentation. The Q&A function will be available at all times. So if you have questions, you can submit them straight away. The question will be visible to everyone. And if you would like to submit question anonymously, you can use the chat. In that case, the messages will be visible only to the hosts. And if you wish to ask question, you can also raise your hand or include a comment about this in your submitted question. You can also use the live stream on YouTube to submit your questions, but we encourage you to use Zoom. Having said that, let me introduce our first speaker, who is Gillian Wright, and she's a director of the Astronomy Technology Center in the UK, in Edinburgh. And she's also a European PI for the James Webb Telescope MIRI, so the mid-infrared instrument. And she will give us an update about the James Webb Telescope. So please, Gillian, the floor is now yours.
Thank you. I'm just going to share my slides. Is that working? Oh. Worked a minute ago. There we go.
Yes,
we okay?
We see the slides. Yes.
Okay, so thank you for giving me an opportunity to talk to you about the James Webb Space Telescope. So I'm going to talk a little bit about the project and some historical things about it, and the MIRI instrument, because that's where my responsibility has really lain, and then commissioning. And I think you've probably all seen the exciting first images, and I'll just talk a little bit about some of the science with a little bit of an emphasis towards what MIRI's been doing in the last couple of weeks. So in 1997, that was when ESA really started doing early instrument design studies and thinking about what the contributions might be to the James Webb Space Telescope mission. And they formally joined the mission around 1999, and that was when kind of design work really began in earnest. So construction began around several years later, 2003, 2004. And while the project was already into construction before the final conclusion that ESA would definitely provide the Ariane 5 launch was reached in 2005. So mirrors getting made. The MIRI instrument was actually the first one that was delivered to NASA for integration with the telescope. That integration and test process took a long time. It's a big telescope and lots of complicated instruments to integrate. So it wasn't until 2016 that we went into an end-to-end testing of the observatory at cryogenic temperatures, and then launch on Christmas Day. So it was an absolutely perfect launch and a flawless deployment. I think this is still one of my favorite JWST pictures because it was really unexpected that we would see the solar panels deploy before we lost sight of the mission, and it was kind of quite nice to see it drifting off towards L2. Well, not so much drifting off as powering off on a perfect trajectory. So that perfect trajectory on the launch has extended the fuel lifetime of the mission really significantly, which is great news for science. So it has been many years in the making, and some of the challenges have had a lot of publicity along the way. I think it's worth remembering that it is really one of the most ambitious projects that we've done in astronomy and space science to date. It's a huge telescope. It has a 6.5-meter diameter primary mirror. But I think the more challenging thing is the size of the sunshade. And the sunshade's made of mylar. It's incredibly difficult to handle. It has to be tensioned just right. All of it had to be deployed in space. There were a lot of really big engineering challenges that JWST has now broken through and demonstrated how to do. And so the passive cooling is working fantastically well. The entire, so this is the first infrared space mission that has had no cryogenic coolants on board. So there's no running out, warming. It won't warm up because we run out of cryogen. So that sunshade is really doing its job. It's cooled the whole observatory to 40 Kelvin. The telescope had to be deployed and aligned and phased in space. So the whole issue of segmented mirrors, phasing of the segments was a real challenge. The cooler for MIRI, so MIRI is cooled to 7 Kelvin. It brought its own set of technical challenges for the mission to go so much colder and achieve the mid-infrared performance. The cooler is not one of the worries with closed cycle coolers is that they're fridges, and there are pumps, and pumps, as we all know, vibrate. But actually, it again is been demonstrated now to be properly vibration-free in flight. And the instrument capabilities comes with a full suite of instruments, more akin to what you would normally see on a large ground-based telescope in terms of their complexity and the scope of the different observing modes that they support. So the European role has been the launcher, obviously, the NIRSPEC and the MIRI instruments. MIRI, I'll say a little bit more about MIRI in a minute. It actually isn't a purely European instrument. It was a European-US collaboration that was needed in order to get that fourth mission instrument, especially with all the technical complexities of different detectors needing to be much colder. And ESA are now part of the STSCI Operations Center for the mission. So what really strikes me about this slide of who's all involved is the number of companies from around Europe is almost comparable to the number from the US that have been involved in different parts of building the mission. So it is truly a big international collaboration between the US, Europe, and Canada. MIRI, the mid-infrared instrument, was in the end agreed that it would be a 50-50 partnership between Europe and the USA that would provide that. So I am the European PI for MIRI. In the US, that would be George Ricci. And we've worked together to make MIRI happen. And in Europe, MIRI was done in what I think is fairly classic collaborative consortium way, as through additional members state contributions. So each country funded their own contribution to MIRI. The UK led, and then that was half of the MIRI instrument. JPL provided the detector systems and the cryocooler, and we focused on the optics and the performance of the instrument in Europe and building it here. So MIRI is a little bit unique amongst the JWST instruments because there were only really the resources to put one mid-infrared instrument on the mission. We provide spectroscopy and imaging and coronagraphs, and we've got more than one spectroscopy mode all built into MIRI. But this slide's a nice summary of the sophistication of the instrument suite that's provided, different techniques, aperture masking, as well as coronography, for example, for looking at planetary systems, wide field and sensitive imaging, more than one way of doing that, more than one way of doing near-infrared spectroscopy of faint galaxies, and then MIRI bringing the mid-infrared science. So we've had to commission all of that. There has been 6 intensely busy months. The first half of the commissioning period since launch was really taken with aligning the telescope and commissioning the telescope optics and cooling MIRI down. It took us a long time to get cold because we had to wait for the observatory to get to 40 Kelvin and then turn on our cooler. There was a lot of cryogenic instruments bring up, you need to take an awful lot of care around ice, for example, not getting ice on your optics. So the whole cool down is quite a difficult thing to control. It all went perfectly well. And then for the last 2 months, May and June, we're just incredibly busy with the first commissioning data coming in. And that was very exciting as well to see all the data. But it has been a very busy period to get everything working as well as it is. And this, you will have seen this image probably in the press releases from NASA you may have done, showing the alignment of JWST. It also shows how JWST can take data in the instruments share the field of view of the telescope. And what that means is that you can observe with the instruments all in parallel. And this is a field in the Large Magellanic Clouds that we used for astrometry, but it is actually showing you the correct view of how JWST, with all its instruments turned on at the same time, would take images of the Magellanic Clouds. And if you look closely at it and you look at the MIRI image, you can see the dust emission in the MIRI image, and you can actually trace that dust lane all the way across with your eye to the dark stripes that you see in the NIRCam and the NIRIS instruments where the dust is blotting out the starlight. But with MIRI, you're seeing the stars through the dust, and you're seeing the emission from the warm dust itself. So this is the sharpest image of a star that's ever been made. The large ground-based telescopes can't do this because even with adaptive optics, they are still somewhat limited by the atmosphere. I think it's showing you what happens when you have a hexagonal mirror, but that's fine. We knew about that. There are little galaxies everywhere in this image, and that was part of the story of commissioning. I think we were finding little galaxies everywhere, sometimes in places that we didn't really want them because we were trying to measure accurate point spread functions, and little galaxies would pop out. And I think there's a paper now on Archive from the one of the commissioning teams with us where they really serendipitously discovered a new galaxy. So it's the observatory is working extremely well. There are some stray light features that were unexpected in all the instruments. There are many things that are working far better than expected. There's detailed information gone out to the community about the performance. It's also on Archive if you want to go and look at it in a little bit more detail. This MIRI is really proving that it's doing what we said. This was one of the first comparisons that was put together of what a change having a mid-infrared capability on a big telescope like JWST in space makes in terms of both the sensitivity and the spatial resolution. So it's comparing previous mid-infrared data in Magellanic Clouds with what MIRI can see. And it's probably about my favorite image. So it is a huge leap in capability, and it very rarely happens this big a change is made in the history of astronomy. So although I'm going to talk about science and some of the science we expect to do, I think the thing that's going to be really exciting with JWST is the science that we don't anticipate and the new discoveries. So the leap in sensitivity, and in Mary's case, combining that with the massive improvement in image sharpness and spatial resolution, it is the equivalent of if we had Galileo's telescope and then we suddenly had the VLT. In terms of the change and the scale of the step, and we didn't have any of the half-meter sized telescopes and 1 meter telescopes and all the rest of them that have been built along the way over the last years and years and years of building up astronomy knowledge. So I think, you know, it's a huge leap in capability that has been made, and I think it will do transformative science for that reason. So the capabilities of the instruments, they all have a very big dynamic range. So we can observe bright things from the solar system all the way out to very faint first galaxies. And the instrument suite was designed to put together a mix of capabilities so that when the creativity of the worldwide astronomical community gets going on what science they want to do, the instruments are there to enable that with many different modes, many different ways of doing spectroscopy or imaging. And I'm just going to talk about a couple of examples that I think are going to be particularly important and in the first year of science operations. But before I do that, it's interesting to look, in fact, at this is the type. So the blue on this chart is applications in different areas of science. And then the red is what the peer review panels actually awarded in terms of time to use the telescope. And you can see that it really is spread throughout the questions in modern astronomy, from our solar system, star formation, stellar death, how galaxies form and evolve, and of course exoplanets. So it's a very broad range of science that will be done in the first year of operation. The other thing that is interesting about it is the importance of spectroscopy. And so if you instead of breaking it down by science area, you look at the telescope time that's been awarded for the first year of operations in terms of what techniques are being used. 70% of it is different spectroscopy techniques. And I think that is quite interesting. So thinking of spectroscopy techniques, one area of science that was a very big bar booming through, and that was exoplanet studies. And the reason for that is I think it's really going to open up a new era in doing exoplanet transit spectroscopy and starting to actually study the exoplanets and understand the chemistry of what is and isn't happening in their atmospheres. So this is a simulated spectrum of the exoplanet that is getting the most attention during cycle 1 of JWST time. It's a sub-Neptune type planet. There's about 80 hours of time invested in this. So this is a simulation of what at the end of that the transit spectrum may look like. The reason so much time is being expended on it is because it's known from some Hubble data that there is something that is probably a water vapor absorption feature in the spectrum, but they have only a very, very small piece of spectrum around 2 microns, and the water lines are, unless you have a much bigger spectral range, the water lines are degenerate with things like methane. But because there's a putative detection of water in this planetary system, there's a lot of time going to be invested in studying it properly. It's not the only exoplanet atmosphere that will be getting looked at, but it's certainly one. So this was the NASA image that was released of the first JWST exoplanet transit spectrum. So the way these spectra are done is what you're doing is you're measuring the transit depth as a function of wavelength with a dispersing element, obviously in your instrument. For MIRI, we have a mode, a low resolution spectroscopy mode that's implemented with a prism in our filter wheel that's designed to do this kind of science. And we also have some data, although wasn't in the first release. This is some commissioning data. So this is actually the first MIRI transit. It's of a super Earth called L1689b. It's about 4 Earth masses. We chose it during commissioning because it's a very challenging object to do. That transit depth is about 500 parts per million, so it's very small, and it was very straightforward to do. This data has not, one of the things that I think is a real transformation with JWST in its capabilities is that it is making some things that people have had to work very hard to get the data and to get the data right, much more straightforward. You can see in the top of this graph, the transit depth is already visible just in the raw data. So we haven't, there's been, there's a slight, very slow, the detectors on JWST are very stable, which is one of the things that is difficult about doing this kind of science with Hubble and with Spitzer, is drifts in the detectors. And you can see in the MIRI data, there's almost no drift, and very straightforward to take it out and then fit to the planet. Like I say, that's about 500 parts per million. We've demonstrated from the residuals that we should be able to get down to 50 parts per million transits with MIRI during cycle 1 observations, which is, is a real demonstration of the power JWST has for this kind of science. So kind of moving much, much further away, the other very large fraction of JWST time that you saw in that graph is in the study of how galaxies form and evolve. So how star formation changes galaxies, how stellar mass builds up, and how the whole chemical enrichment of the universe, what the metallicities of the galaxies are and how they change with time. And there's a lot of time awarded in the cycle 1 programs to look at this and to really push back to the epoch of reionization and the first galaxies and stars that formed. And so this is the deep field that was released. There are many papers on arXiv this week, a lot of excitement about this data and some of the early release science programs that are ongoing. Number densities of galaxies seems to be much higher than expected at redshifts. There are claims of papers of more than one galaxy 5 sigma at redshifts in the 13 to 20 range. Definitely enough, I think, to be saying there are discrepancies with models. I would point out that the papers, of course, have not been peer-reviewed yet, and also that this is not yet very deep data. So the data that this is going to, the depth of the images that are being analysed currently, they're going to about 29th magnitude, so they are going deeper than Hubble. But the plan with the cycle 1 observing time is to get 2 magnitudes deeper than that still on the same region of sky as the Hubble deep field. So I think there's a lot of excitement coming there. And nearby galaxies, this is my favorite MIRI image. So on the left, you have the Hubble image of Stephan's quintet. On the right, you have the MIRI image, and I think it just so demonstrates the difference it makes to be able to look at galaxies in the mid-infrared. What you're seeing here is the streamers of star formation. And the active nucleus in the top right galaxy was known about from X-ray data. It's a Seyfert 2 galaxy, so it is heavily obscured. And as you can see in the mid-infrared, moving to the longer wavelengths, there's a diffraction limited point source image in the middle of that galaxy. So when we're really seeing in the mirror image the star formation in the tidal tails created by the interaction between the galaxies. And to follow that up, we have mirror spectroscopy. This is done with our integral field unit. Integral field unit spectroscopy is still relatively new. It's certainly never been done in the mid-infrared before. So what you are able to do using image slicers is to take simultaneously spectrum and image at each wavelength within that spectrum. So what's shown here is the reconstructed image from the mirror image slicers of the active nucleus in the Stephan's Quintet galaxy. And then you can take within that image is a data cube. So because you can then extract spectra for any point in that image. What's illustrated here is the big difference between, so if you're looking immediately in the region of the active nucleus, what you're seeing is the dense obscuration here around it. So you're seeing the silicate dust, the dense molecular hydrogen lines of the obscuration around the nucleus. If you look a little bit off nucleus, where there's some evidence in the X-ray for a jet, what you're seeing is the ionized gas that's being heated by the active nucleus. We know that so the neon lines that have been detected in this mid-infrared spectrum, the excitation of those neon lines is high enough that it's not stellar radiation. So this is not star formation that we're seeing here. This is actually the AGN heating the medium in the nucleus of the galaxy. So I think, again, is pointing to the exciting science that we're going to see coming in the coming year and future years from JWST. So if I was to summarize it, I would say the performance is exceeding expectations. The spatial spectral resolutions and the sensitivities have already been shown in the commissioning data and the early release observations to be transformative. It is going to provide a new view of the universe, and astronomy is an observational science. So, you know, when we go and look, that's when we discover new things, and it's ready to go. So I would like to say a big thank you to the MIRI commissioning team. They're responsible for having taken most of the data, the MIRI data I've shown you today, and also Roberta Maialino and Sarah Kendrew generously shared some of their slides. They've been giving similar overview talks in the last couple of weeks. So thank you, everybody.
Thank you so much, Gillian, for a nice talk, and we are all awaiting the amazing science that James Webb will deliver. So let's take questions now. We have already a few in Q&A box, but I encourage everybody to continue submitting questions. We have several minutes for this. So the first one comes from Alexander, and he asks, GWST has this very distinct 6-edge star PSF. Why is that not removed in the images?
I think it could be removed in the images, and in fact, if you look in Hubble images, they usually clean diffraction spikes out. In fact, because JWST is truly a diffraction limited telescope at all the wavelengths it's used at, the diffraction pattern changes as a function of wavelength, and so it will take some time to develop the algorithms as a function of wavelength to take the diffraction pattern out, but I'm sure we will start seeing images without it. And I think it's very pretty. And if you're looking at your data, you know, yeah, sure, you take the diffraction spikes out, but you better know you took a diffraction spike out if you're looking at a faint galaxy behind it.
I agree. Artistically, it looks very pretty indeed. So the next question is from Heis. And he asks that you said that the near perfect lunch results in a longer science time. And do we already know roughly how much more time is that?
From the point of view of fuel, the spacecraft fuel should last for at least 20 years, which is roughly double what was expected, or double what had been planned for. So the lifetime really, I think, will be limited in the same way it has been for Hubble in terms of what the lifetime of other parts of the mission are.
Thank you. The next question comes from YouTube, from Simon. He first of all says that your talk was great. So,
thank you.
And he's curious about what data policy you have, and will raw data be released, and is there an embargo?
So the raw data is released. There are two types of JWST program. There are some programs called early release science and director's discretionary time. And for those, the raw data is made public instantly. Well, within a few hours. By the time it comes to the ground, it's processed through the pipeline and then is made available. So within hours of it, everybody gets the data at the same time. And then the guaranteed time observations of the instrument teams and the programs that have been competitively awarded time, they have the raw data has a proprietary period of 1 year. And then it's all public.
So I don't see any more questions, but we have some time. So let me also ask a personal question. So you participated and designed the MIRI instrument, and I'm wondering what was your personal scientific question that you wanted to address with that instrument?
Star formation in relatively nearby galaxies. So galaxies around from the current epoch to redshifts around 2, where there's a lot of star formation, and what the feedback is between when you have an active nucleus, what the feedback is between the interaction, which you can't really see without looking in the mid-infrared to understand how much of the luminosity of those galaxies is coming from the star formation and from the active nucleus. And I think that's still one of the things that interests me, but MIRI was designed to do a lot of other science, and I'm excited about all of it.
Sure. Okay, so we have another question. From Sasha. I would imagine that the amount of data is quite large. Is the downlink limiting the amount of data you get, or did you get around that with the onboard process? And very great talk as well.
There's very little onboard processing of the data. It's all coming down to the ground, pretty much.
Okay. We still have some time if you guys have question. Yes, Jean-Baptiste asks, are the data continuously downloaded to Earth?
No, there's contact. I think it's once, I'm not sure if it's once every 24 hours or once every 12 hours. During commissioning, there was more contact than there will be in normal operations. So I'm personally a little bit confused by that, but I think it's once every 24 hours.
Okay.
Valeria, may I ask a question?
Sure.
I had a question about, well, firstly, Gillian, thank you. That was a wonderful talk. And a question about MIRI and the other instruments, that the image you showed about them all in the same field, and you mentioned how they had all been used in parallel. Is that commonplace for them all to be used on the same field, or is that a special occasions type thing? When I saw the slide about how you'd shown the project time for the different instruments, looked like the MIRI coronagraph was limited, and I can see how that wouldn't be used commonly. But will it be common for both the NIRCam and such like to all be used at the same time?
So one mode that is commonly, so the graph showed you what we call the prime instrument. So when you write your telescope proposal, you say, I want to do MIRI imaging of this, and then I'm going to turn the NIRCam on at the same time. So the deep imaging, an awful lot of those programs are using both MIRI and NIRCam in parallel, and then because they look at neighboring areas of the sky, you have to think about how you plan out your mapping if you want to have simultaneous near and mid-infrared data on the same source. But in general, the deep field imaging is being done by using the instruments in parallel. And with MIRI, we're using our imaging capability sits in parallel to our integral field spectrograph. So a lot of our programs are, even where we're doing integral field spectroscopy of faint high redshift galaxies, we've also got the MIRI imager turned on, and in some cases NIRCam imaging as well, doing deep fields in parallel. So that kind of parallel observing is going to get used a lot.
Thank you. There's some other questions flooding in now.
Yes, so one other question from Jean-Baptiste. What do you think are going to be the first big and exciting new result that will be published in the coming month?
I think it will be something like methane in an exoplanet atmosphere. That would be my guess. Although I would have to say that the extragalactic community are being very, very busy at the moment analyzing those deep field images.
Thank you. And let's take one last question from Martin, who also says, fantastic talk. Can I ask about the typical cadence for detectors' discretionary time observations? How quickly and easy will it be possible to deploy the telescope to observe optical sky location? Not so relevant for LISA perhaps, but important for example, follow-ups for binary neutron stars direction by ground-based gravitational-wave detectors.
Yeah, so there is I think so there is a way that you can request a target. We call it a target of opportunity for that sort of thing, and there is time held back in the planning of the cycle to enable that to happen. So you can put in a target of opportunity request at any time during the semester, and they'll look at it and see how quickly they can respond. But the director's discretionary time, there's a call out every year that happens partway through the observing cycle. So there's one just gone out now, for example, which can be, you know, that something that you only need a very small amount of time. Not necessarily something like a transient, but something somebody's thought of after seeing how the observatory is working, for example. I think would be considered that. Although I would have to say that I have no responsibility for policies. They sit with the Space Telescope Science Institute.
Sure. Okay, so I think we exhausted all the questions. So let me thank you again for an excellent talk and very clear, exhaustive answers on behalf of everyone. And we will now move to our next speaker, Victoria Grinberg, who is a liaison scientist at ESA. She's an expert in X-ray binaries, but today she will talk about astronomy and climate crisis, because she's also at the core of the team of astronomers for planet Earth. So Victoria, please, the floor is now yours.
Perfect. Thank you so much. And thank you for giving me the chance to talk about this particular topic. And thanks everybody for being here and being interested. So I think this talk unfortunately comes very timely if you look at what the weather looks right now and the big discussion whether this is actually influenced by climate. And what I've shown on my title slide right now are images of the Sentinel satellite, and the 5 of the 6 newest ones are actually all images of wildfires somewhere in Europe. And I really hope nobody of you is affected, nobody of your families is affected. But even as somebody sitting in the Netherlands right now where things are comparatively cool, this is, to be honest, just like really scary. So what this talk is, well, what this talk is not an introduction to climate crisis and to climate sciences, because I'm an astronomer, I'm an astrophysicist. What this talk tries to be is to start a discussion. And my ideal outcome of this talk is if some of you go back to your home institutes and make changes, start thinking about changes, start implementing them. And what's important about talk like that is who is actually talking. As I've been already introduced, I'm liaison scientist at ESA STEC. I'm a high energy astronomer from my background, so some overlap with ground-based gravitational wave observatory science. But when I'm giving this talk, I'm actually giving you it in a way from very different points of view. I'm a citizen who wants to secure my own and my fellow humans' future. I would love in 50 years to have a livable Earth. I'm a scientist who wants to secure your field's future, because there'll be no astronomy if we all spend our time just fighting climate crisis because we haven't done anything for the next 10 or 20 years and things have really deteriorated. I am, as has been mentioned, one of the founding members of the European Science of Astronomers for Planet Earth movement. But at the same time, I'm also a group leader responsible for my early career researchers in my own group. So when I'm making an argument for like, we should all make just remote conferences, I also know that my PhD students need in-person interaction in order to further this career. And until very recently, I've actually been an early career astronomer myself. It's always a little bit easier to make arguments from a secure permanent position, but I've also tried to do them when I was an early career researcher. And as a second point, why I'm talking about this is a slide from Gregor Hagedorn, who is one of the founding members of Scientists for Future, who are there to support Fridays for Future with like really the scientific background. And it really summarizes why I'm giving talks like this. So what he wrote is whether we as people who do science or who communicate science are quiet or speak, both is political. And this is why I'm getting out and putting myself in this uncomfortable position of talking about climate change instead of talking about my science. So why should we as astronomers care? And why this in times of COVID or also in times of war? And the reason is, well, we have crises right now, but what is coming is in the end even more extreme, as this like lovely cartoon shows. And just to tell you, to show you two different numbers. So we really need to act right now. So this is a carbon budget that we can use in order for our climate to just warm up by just 1.5 degrees. And you see that it's being used up, and it's being used up mainly by Europe and the US, recently also more by China. And it's used up faster and faster and faster. In particular, if we look at the CO2 budget and how much the world is emitting, and this is a paper back from 2017 when they looked at what is the CO2 emission equivalent in gigatons per year, and how much do we need to reduce it in order to have a temperature increase of only 1.5 to 2 degrees. And you see different curves, and I can tell you we missed the blue one, we missed the yellow one, we are also about to miss the red one. The one that is pretty much means that, like, we need to stop emitting CO2 in order to reach our goals in terms of limiting how much warmer Earth becomes. So, of course, this is not just a problem of us as astronomers and physicists. So why should we, who are mostly thinking about exoplanets or black holes or other galaxies or AGN, why should we think about that? First of all, we are the ones who are causing CO2 emission, and most examples that I have are from astronomy, because this is what I worked on, this is what I know best. And there are a few reviews, and I'm going to look into some of them in more detail, looking at individual institutes, looking at our conferences, looking at whole countries in the case of Australia. We and our work directly suffer from climate change. There's some look at the atmospheric conditions of telescopes. There are multiple examples by now of observatories being affected by wildfires and similar. And last but not least, the public is fascinated by astronomy and, well, at least some parts of physics, and gravitational waves is very much part of that. So when we are doing outreach, our audience trusts in us as experts. If you see the impact that James Webb images have had worldwide, who have been really everywhere on title pages, to be able to ride this wave and to also include a little bit of climate change outreach. This is like really a unique chance that we do have. So numbers, just looking into some details of how much impact are we actually having, how much CO2 equivalent are we producing, how can we reduce that? The total CO2 footprint per astronomer for work-related activity, depending on seniority, how much people travel, and so on, how much, whether they do computational work or not, is 5 to 40 tons per year. The European Fit for 55 pledge is that on average, each European citizen will spend just 3 tons per year for both work and private activities, which means that astronomy is above that just for work. I'm sorry, I think did my connection just break? No, I'm back. Sorry about that. And one really important point there is also that if we look at who is actually producing CO2, it's actually the top 10 to 1% of 1 to 10% of earners who produce most of CO2, and most of us scientists are in this area, are not in the bottom 50% of earners. This is worldwide. So how much emission is actually a given astronomy institute producing? So this is an example from Knut Janke et al. It was a Nature Astronomy publication in 2020, where they looked at the greenhouse emission from the Max Planck Institute of Astronomy in Heidelberg in Germany, and have really broken down of what has been going there. So the total CO2 emission per researcher was 18.1 tons. About half of it came from air travel, and about 30% of it came from electricity. Another 16% was heating, so oil. you can compare that worldwide. You can, for example, compare what MPIA is using right now with the German pledge for 2030. So this is how much on average a German citizen should be spending until 2030, that is 6.8. So MPIA is spending, again, just for work, about 3 times as much. You can, of course, also compare with a different example, which is Australia, which is spending more than twice, which is producing more than twice as much CO2 equivalent per astronomer researcher, and where electricity plays a much larger role in percentage of the total CO2 production. This is due to the fact that most of the electricity in Australia is coal, while quite some of the electricity in Germany comes from renewables. So there's also a question of the electricity mix that you have in there. When we are discussing electricity, one big thing to discuss are large computations, and there are people working on that. I'm not going to go into detail in there because I'm not an expert. I'm just going to mention that this is something that we also need to start thinking about. Where does the electricity for our supercomputers come from? Can we reduce electricity consumption there? Can we think about what can we do about cooling? What can we do about the electricity mix that is used in there? But what I'm going to look more into detail, because this is something that I myself worked on, are flights and travel and how much impact they have. So again, looking at the Max Planck Institute for Astronomy, and if you look at the amount of emission that comes from different flights, you'll see that the most emission actually comes from long-range flights, from flights to North America and to South America. Flights within Europe contribute to the total flight emission, but contribute just about 10%. And those are the only ones that can actually be done by train. So we need some other kind of solution that does not just take the train for all the trips to North America and South America, whether it's reducing the trips, whether this is combining the trips, whether this is something else. There are quite a number of other ongoing footprints and audits. If you're interested in, there's an ESA cardboard footprint that has been done by Carbon 4, actually outside company. There are more details on the Australian astronomical community. The Spanish Astronomical Society has also looked into that. I don't speak Spanish, so I'm not sure whether this has been published or not yet. So there is many different societies and institutes looking into where does their CO2 come from in order to be able to then address the problem. And the other big point, and this is where I have to say, well, thank you folks for organizing this meeting as remote, is the carbon footprint of large astronomy meetings. It can as well be carbon footprint of large biology meeting or carbon footprint of, I don't know, large physics meetings. And just to give you an example, this is European Astronomical Society meetings, so they used to be called EVAS. And this is actually how I started my work in this field, because EVAS 2019 was in June 2019 in Lyon in France, when France experienced an extreme heat wave with national record temperatures reaching 46 degrees and temperatures in Lyon reaching like 44 degrees. It's not fun being at a conference when it's 44 degrees outside and you are in a university building under the roof with no air conditioning. It is miserable. And it's kind of like, for me at least, it was a wake-up call asking, well, okay, but we are also here in Lyon. Are we perhaps part of the problem? So what we did is we did a questionnaire that the organizers nicely allowed us to send to the participants. And we had quite a good number of people who answered. So about 300 people who got back to us. and who actually told us how they got, from where they got 2 years and how they got 2 years. So what mode of transportation they used. And you see, and this is kind of like expected, that quite a number of people were more or less local. So those are the people who came from France or from close by places in Germany by train. Then you had a number of people from other places in Europe, a number of people from the US, for example, and then a few people from Australia. And you also see that again here, most contributions are actually from long-range flights. This still, because this is interesting, we looked into how people who were comparatively close by to Lyon, who could have taken the train, whether they took the train or they came by plane. And that's also like even people who just need 8 hours to get to Lyon were partly still flying, which is part of the problem, of course. So we had the data from the 2019 meeting, and then COVID happened, and the 2020 meeting was fully remote. So we actually had a comparison. So what we did an estimate of the carbon emission for years 2020, which was remote because of the pandemic. So we estimated network-related emissions, so computers and so on. We network and so on. We estimated laptop-related emission. We estimated Zoom server-related emission. And the point is that this emission, so you see cumulative CO2 emission just from travel was at about 200,000 kilogram. And if you look at the total emission here, we are not even at a ton for a full meeting. So the reduction is, of course, extreme. So is the solution online-only meetings? An argument for online-only meeting is, of course, environmental impact, is also accessibility, which is not something I'll talk about, but something I'm going to show you in a second where to look up more. The disadvantages is, of course, it's much harder to have in-person interactions, even so there are some ideas with, for example, 3D, with local hubs, and so on. And spontaneous communication is, well, not quite as likely to happen at a remote meeting. Also, we should also ask ourselves, can we facilitate that in some way? So to me, this means we need to find a balance. And what is also important, we should not confuse emergency online meetings with online first conferences. And what we have done for the last 2 years has often been emergency online meetings, are meetings that were supposed to be in person, and people realized, okay, people cannot travel, so we are gonna do that online. This is not the same as a meeting that is planned to be online first. For example, people tell me, well, why usually if you ask people why you're going to meetings, they're going to say, I'm going to meetings for all the spontaneous communication, for the coffee break, for the lunches, for the dinners with the colleagues. And then if you look how an online meeting is organized, and it's talks, and no time to actually interact. And that tells you that we haven't actually thought how to do an online first conference that emphasizes what people actually want to get from a conference. What's also important, and I will show you just one thing, is accessibility. So I gave a similar talk, well, one focused on travel at the International Cosmic Ray Conference 2021, who gave me their numbers. So for 2019, that was an in-person meeting. International Cosmic Ray Conference was in Madison in the US, had 850 participants with about 1,100 abstracts. And people from at least 2 countries, and I'm not going to name them, but 2 big countries had giant visa problems. So there were pretty much no people from these countries attending. Compared to that, the International Cosmic Ray Conference 2021 in Berlin, remote, almost doubled the number of participants, had people from more countries attending, and especially from underrepresented countries attended, and also had more abstracts submitted. And as last point, to like, if you're really interested in topics of accessibility, there are like a lot of discussion also from the disability community, from many different communities. Dr. Sarah White gave an amazing talk at the EIS 2021, not ESA 2021, called An Environment for Everyone. If you really want to find the link, you can also write me an email that can point you towards it. She's very focused on why we should do remote meetings. What's also important is not just that we assess how much environmental impact we are having, but that we actually start thinking about it before we build our instrumentation. And here again, there's at least one really nice example I'm aware of. This is the carbon footprint study of the GRANT project. So what they try to do is, so they're starting off their project. So they started with a carbon footprint audit of the different phases, and they started thinking about how to design collaborative practices and instrumentation to minimize the carbon footprint at the same time while enabling cutting-edge science. And what I found especially interesting there, so they look at, so in 2021, they have a prototype. In 2025, they had the Grant 10K. And somewhere in 2030, they're having Grant 2000K. And if you're looking how the different contributions develop with time, what is contributing most to the overall budget changes? At the beginning, you need to travel a lot. Later, your travel may remain the same, but your things like data storage, data analysis, data transfer eat a ton of time. And there's something that, like, for us in space may play a lesser role, but for example, stainless steel, if you're actually building your project on Earth, that is a major source of CO2 impact, of CO2 that you need to take into account. So this is an example we can start thinking, and we need to start thinking about what we are doing from the very beginning. What you can do is, if you have to organize meetings in person, you can try finding a location that's ideal. And there's an example from the Athena XIV team where they have actually developed, and it's an open access tool, a travel footprint calculator for collaboration. So you pretty much enter how many people are coming from where, and where you want your collaboration meeting or your conference to be. And this thing is going to tell you how much CO2 this conference is going to cost you. Interestingly, also depending on different online calculators, because they give slightly different results. So you can also, like, if you need to meet in person, you can at least try to find a location that minimizes CO2 impact. So conclusions for the first part, and then I'm going to address one more topic that's somewhat interesting, is to reduce our carbon footprint, we need to understand what our main contributions are. They are not always obvious. The understanding our carbon footprint is actually a major research project in itself. So our Nature Astronomy paper, for example, for conferences, did cost a significant amount of our time. And to be honest, we as astronomers are not always experts to do that, especially, well, for conferences, we can. If we're starting looking into, for example, large hardware projects, things become a lot harder. And this is also important to me. There are limits to individual action. We can say I personally can say I'm reducing my travel, but it would be much easier if the changes were systematic, if the way we organize conferences, if the way we organize our collaborations would change. So that's part that we are kind of like doing as astronomers, looking inside and looking into our own field. And in the second smaller part of my talk, one thing I would like is to look outside and I already mentioned that as astronomers, we are trusted by the general public. So the idea is to use this trust to, if we feel comfortable, or if we don't feel comfortable, but we still want to try, how to communicate astronomy to communicate climate crisis outside. Oh, wait. I wrote the wrong direction. Okay. And there's, again, a nice paper, again, in Nature Astronomy, 5 steps for astronomers to communicate climate change effectively. So Alison Anderson and Gina Maffrey are actually both people working on communication. So Alison and on climate change communication, who worked on kind of like trying to think about what can astronomers do. And the way we can do that, we have to tell stories, because to touch people, we need stories. People are not gonna remember numbers, scientists gonna too, but like not usually the general public. We have to make it relevant to people. So to really touch their lives, to make them feel it in a way. We have to tailor the message. And you certainly know, depending on if you're giving outreach talks, depending on whom you are talking to, your message is going to be very different. And an interesting point that this particular paper, for example, makes is there are 2 approaches to thinking about climate crisis. You can make an argument making on altruism, based on, well, the world is going to be in a bad place. Don't you want to improve the world? This argument is not going to work with a lot of people. With some people, the argument you have to make is, this is going to impact you and your work most, and you need to do something, because otherwise you will not be able to reach your particular goals. And this is on an individual communicator to find the right way. We need to focus on solutions. And I'm also trying it a little bit in this talk. And it's easy to talk about things, about the doom and gloom of it, about what everything is going wrong. But that often leaves people feeling that there's nothing they can do. And then they say, well, okay, everything is so bad anyway. I'm just this little small person sitting here. I'm not going to be able to make any change. So I'm not even going to try. And this is not what we want to do, what we want to cause. And we also need to embed the change in astronomy. So to change our own behavior and to change what goes on where. As a few general sorts of things we can talk about. We can talk about facts and methods. We can communicate climate change from the neutral ground. We can, for example, communicate physics, communicate nature science knowledge, talk to people about the scientific method, so they have a way to understand how science works in general, and also how climate science works. We can talk about astronomical influences on climate, because there are a lot of people who say, well, it's all just kind of like our sun changing how it's behaving. And it's not man-made. We can talk about perspective. So kind of like the idea of the pale blue dot. So this is this tiny dot over here that is Earth. The idea of astronomical scale, global citizenship, Earth as being like really unique. All those are things that we as astronomers, as a physicist, are really qualified to talk about, where that we are talking about anyway. And we can include a little bit, some thought on how fragile our Earth is, how fragile our ecosystem is, what we can do to protect it. And one important point is Abe always triggers empathy. So the idea of the sublime, the idea of those like wonderful, the idea of hearing the chirp from the gravitational waves, of having black holes coalesce together, or the image of just like our Milky Way, the way it is shown here by Juan Carlos Munoz, it triggers empathy in people. It triggers the idea of like, okay, maybe this world is worth it. It's worth actually trying to save. And last but not least, storytelling. So fascinations triggers interest, and we could always look into cross-field research and like stories that trigger empathy and involvement. And this is like a really lovely example from the Antares telescope that does neutrino detection and studies whales, and studies also the influence of the warming Mediterranean Sea on the animals and fish that live in the sea. So if you can make connections like this really touches people. That's really a way to bring the topic to them. And you can, of course, also include climate change in teaching, whether you're talking about habitability, whether you're including climate as part of introductory physics and astro lectures. This, of course, depends on your university and your curriculum. But for example, we have done that in our introductory astronomy lecture. We talked about the greenhouse effect when we talked about the planets of our own solar system. You can talk about the physics of climate change. You can talk about the recent Nobel Prize from 2021 that was at least that was partly for climate science research in the end. And I have quite a list of additional resources. So there are really good papers by Vanessa Moss looking at how to do good online meetings, which I at least found really insightful, that helped me organize good online or like better online conferences. There are like a ton of resources online on archive, different groups looking in how to do things, partly also as part of the decadal survey in the US. You can think about what we do in Astronomers of Planet Earth. So what we do, we have a supporter list, a mailing list, have webinars, try to use social media and so on, and Slack to like really connect. So what we are doing is, for example, the two series of comments in Nature Astronomy were like really triggered by us and by meetings that we organize. We do lobby work in different institutions, video outreach material, and something that I find extremely important. We do a lot of networking and emotional support for each other, because like working in this area is actually really challenging, a lot more so than doing like my lovely science. And so these are the two paper series that we did, looking at impact of climate crisis on astronomy and astronomical impact on climate crisis, and then looking a little bit more into communication and what is effective communication, whether we need to do some like political lobbyism as part of our astronomy work in here. And with that, I say thank you, and I'm glad to take any questions.
Thank you so much, Victoria. I know that in the climate crisis context, there is this big question between individual versus global contribution. And I think that you did the biggest thing that an individual can do is to speak to many other individuals. You know, today you reached out to thousands people within the LISA consortium. So thank you for that.
Thank you for giving me the chance to do so.
I'm confident your words will stay in our minds for the future, for the planning of LISA. So let's take some questions now. We have already a few, all come from early career scientists. And since we have about 10 minutes or so, I would like maybe to invite people to actually speak, to make a little bit of a dialogue. So let's start with Martina, because I know Martina can unmute herself.
Yes, okay, you hear me well?
Yes.
Perfect.
First of all, thank you for the talk. It was just my personal curiosity. I saw that you made many studies regarding how much is the emission for the CO2 for traveling. I was wondering if you also start studying compared to actually how much is the emission, for example, for industries, or in general, all other activities that we do and make CO2. So it's actually comparable, the emission that we do by flying, compared to like emission that also developing countries are doing.
Okay, so we did not do direct comparison studies. So if you look at so we did not compare with individual other industries, not even with individual other fields, because such studies don't exist. We have a little bit been of a trailblazers in astronomy. If you look at the general impact they are not going to be huge impacts because like there aren't that many astronomers. But at the same point, so a discussion that is happening in Germany right now, Germany, like there's some people who say Germany needs to reduce CO2. And the German goes, but we are only contributing 2% worldwide. If we are reducing by even by 50%, it's not going to change much. And this is kind of like the argument that is always being made. So this is a complicated argument to make, and if everybody makes an argument like that, it goes like, well, then nobody does anything, because each single contributor is really so little. And for us, for me, it's really about us being an example of how to make things better.
Okay, so for summarize, you see, even if like flying is 1% of the total, you still something. That's what you would try to convey.
Yeah.
Okay.
Okay, we have many questions coming through Q&A. Alistair, can we actually make people speak, starting from Jean-Baptiste?
Oh, we can invite them to unmute. Do you want to start with Jean-Baptiste?
Yes, let's start with him.
Okay, I will try and find him.
Sorry for making you work.
I'm
Yes, I know.
afraid to kind of like to stay around for a little bit of the break if people have questions.
First of all, thanks, Victoria, for this talk. It's very interesting and, of course, a very pressing and important issue. So it's great that you could talk about it. My question was about, it's a very practical one, on the subject of in-person meetings, which still happen. And oftentimes, when you're looking at train tickets, if it's a mildly long trip compared to airplane tickets, it's a lot cheaper. It can be, there can be a factor of 2 or 3. And as early career scientists, especially, travel funds oftentimes are limited, and it can be hard to justify to the administration or your group. Do you have any recommendations about that?
I don't think individual people can, but what we can do is try to implement general changes. Organize yourself into a group and try to make larger changes. For example, until recently, like I spent a lot of time in German academia, so most of my examples are from German academia. People will tell you, you have to buy the cheapest way to go places. And if the train was more expensive, literally nobody could allow you to do it differently. And the only way to change that is really to do like lobby political work, and to really like make societal changes. An individual, especially early career researchers, because early career researchers are in such complicated situations in many regards, usually can't. But if you can organize, if you can start making changes on a larger scale, that's the way I would try to go. And like, don't be discouraged if you like, you have to travel, then you have to travel. I'm doing the same, right? But it's okay sometimes to think, well, I have those 2 trips. Do they really need to be 2 individual trips? Or maybe can I combine them into 1 trip? Then I have like 1 leg less to fly. So small things like that. I wish I had a magic solution. I don't.
Thanks, Victoria.
Yeah, let's go next with the question from Vivian.
Hey, thanks again. I mean, it was really great because I was wondering about this for a while, but I never kind of found it was. I mean, it's so hard in the sea of all this data to see what's actually happening. But I mean, my question was very similar to the one already asked, if there was comparison to other industries, other research fields. But as you said, you didn't do any direct comparisons.
No, it's I said, like, if people actually have no especially other research fields who did similar studies, please point us towards it. We really want to do the comparison. Right now we're standing there alone with our little flag and doing like, hi.
Yeah, I mean, yeah, this would be great to just see if there's other research fields who have done a similar effort, and then you could compare.
I mean, there are other research fields. So I don't know the CO2 estimates, but I do know. So there are there are other research fields that looked into how to do remote conferences, for example. So there's idea with hubs that comes from photonics research, for example.
Yeah.
So there are some areas that have that, but like really the CO2 estimates, I haven't seen any.
Yeah. Interesting. Not even from the environmental scientists themselves. Yeah.
There may be, but
I could ask, I guess.
Let's
Oh, yeah.
let's switch to the question from Simon.
Hey, good morning. First of all, thank you so much. And I loved the quote that staying silent is as political as speaking out. And no one wants to understand that. Like here, like I'm from Florida, especially here, it's like being quiet is a neutral position, like duck and cover, which is horrible. Anyways, my local university here in Florida is about to build a new fossil fuel power plant on campus, university owned, to power our data centers. And I was thinking that after your talk, maybe our astronomy, physics, engineering department could team up and the department leaders could try to step in and like oppose the university leadership. But how would one like convince the department heads to take action?
I don't know. I honestly don't know. And this is the point where I'm more of a scientist than I am an activist or an organizer. I don't know. There are people who do. And my naive suggestion would be look around for local communities who maybe are doing similar work already and talk to them, because there are people who know how to organize stuff like that. I frankly don't. And I have not been myself very successful in changing how some of my own previous institutes behave. What also helps is, and this is not like a scientific reply, this is very much like a Victoria personal reply, is to get individual people who may be on board with you, like talk individually to faculty folk. Like I assume you maybe also an early career person, right? Talk individually to faculty and try to find out who may be on your side, and try to organize with them. But as I said, this is like very much Victoria is trying to find a way around it answer, and not a systematic, this is how to approach those things answer.
So I was hoping the astronomers for planet Earth would have like a professional outreach department to convince department heads.
We don't. So we are. So what I can offer is to join our Slack and to see whether you can find people over there. But we are very much a grassroots things, right? So we have zero funding.
Great.
So all that we have is literally us and us trying to organize in a way that works. So sometimes they're kind of like small things that show up here and there. And we are trying to set up us in a way that would allow us to accept funds. But it's a grassroots organization. Okay. There are people, however, who know how to do lobby work in there. So
I would love to take your funded offer.
Yes,
absolutely.
You can join. You can drop me an email, and then no promises made that you're gonna find somebody, but it's a way to find people with a similar mindset.
Awesome. Thank you so much.
Thank you. So I have an approval from the directory that we can take a few more questions if you're fine with that.
I'm fine with that. I also want to offer people, if you really want to kind of like ask additional questions, please feel to drop me an email. You can easily find my email online or find me on Twitter, which is also a way to get in touch.
So let's then take a question from Jennifer that is relevant to our field. How do we reduce the carbon impact of space-based astronomical observatories, or perhaps alternatively, how do we leverage the inevitable carbon impact to affect change?
Okay, so I should also emphasize I'm not speaking here as an ESA person, right? So this is me being invited. This is not an official stance. I think one important thing is I mean, some things we are not gonna change. I mean, it's a rocket being sent into space, right? So there's gonna be CO2 impact with that. But it is not just the observatories that's being sent in up there. It's also data that is being analyzed. And I can imagine, especially for something like LISA, where people do a ton of simulations, look into what we can do about green computing, for example. So that would be one access for me. And it's also, I really don't have a good feeling for a project like LISA. What are actually the impacts? Is it the consortium meetings? Is it the simulations? Is it, I don't know, maybe some industry studies that are cost a lot of it? I think the first step is really make an estimate where does the CO2 impact comes from, and then look into what of those things are actually realistic to reduce. And also be open about it, because also admitting, hey, we're trying our best, we're still not good, is really important. So it's like, nobody of us can be perfect. This is why I'm always saying, well, I'm also still flying. I wish I could stop, but I'm in a job where I can't. So always find some kind of balance, and also find out what it is that's actually causing most impact.
And from my side, I wanted to add for Jennifer that actually within the LISA early career scientists, we sort of started to talk about this and to look how we can do these estimates. For instance, for computing, it is something that's very doable even without knowing much about the mission itself. So if you're interested, get in touch with the chairs of the group, and Martina will talk about the group later this morning. And perhaps to conclude, we can take the question from an anonymous attendee that asks, do you think that setting an example is enough? Since the situation gets more dire as time passes, should we scientists try to add more pressure in a political sense, whatever that might mean?
Yes. And the answer is yes. But maybe as you have seen to my answer, I think that was to Simon, I'm a more scientist than an activist, even so I'm kind of like in a more activist role right now. So I don't know how. And there are people who much better know how to. I mean, I also, as an interesting point, I also know people, and by now several, who had a hard look at their astronomy careers and decided to change into an environmental science. I obviously didn't do that. And who decided they want to be professional campaigners. They want to professionally work in climate science, or not just in climate science, but actually in environmental protection in some way. I'm not sure it's the right decision. It's obviously not the one that I've made, but it's something to consider, and it's to consider, like, how can we make some kind of impact now, and how much pressure can we do?
Thank you. And maybe just to, finish all the questions, Sasha, very quickly, I think that you can unmute yourself.
Yes, thanks for this great talk. I think or a lot of energy consumption and carbon footprint is inevitable in large observatories and other facilities. So should we be looking at compensation and lobby for having grants, for instance, for that as well?
Compensation is the worst thing one can do. Compensation and also compensation for flights is pretty much what we've done 20 years ago, because the problem is happening. So the question is, it's kind of like it's the last thing to do when everything else is exhausted. And I do think we can change to renewables. We can have a very hard look at. So I'm not an expert in calculation in simulations and high performance computing and so on, but there are actually people working in that area. I gave a talk at the at a particle physics conference where somebody from the particles physics computation who is actually working on green computing, on how to optimize algorithm, also how to build computing centers in a way that is green. So there are ways to do that that are much, much, much more impactful than compensation, because compensation is kind of like a little bit like this religious thing in the history, right? You do the bad thing and then you say, here's a little bit of money and I'm free of sin and I'm continuing how I've done before. The CO2 is out there. Compensation is not actually stopping it from happening right now. So it's like, even if trees are planted, they are not going to be like all big and eating up all the CO2 on time in the next 10 years to actually stop this.
Thank you. So since we're now at the past, let's leave 5 minutes for a quick coffee. And before we break, I would like to thank you again, Victoria, for bringing this very important topic to the LISA Symposium. So
thank you so much. I'll have to log out, but as that to everybody, like if you want to get in touch, please feel free to go ahead.
Thank you.
Yeah, I'll just maybe add that we'll give you 10 minutes of a break, so we'll return at 22. And thank you.
Thanks.
Okay, Valeria, if you're ready, I think we can get started with the second part of the session.
Okay, so welcome back to everyone to our Wednesday plenary session. In this second part, we will have two talks, one on stochastic gravitational wave signals and an update on the LISA early career scientists. Let me remind you that we will take your questions at the end of the talks. You can submit them via Q&A option, and you can do that throughout the talk, so don't wait. Or you can also submit your question privately through the chat, and those will be visible to the hosts only. So let me introduce our first speaker of this second part, who is Nikos Karnesis from the Aristotle University of Thessaloniki. He's our in-house LISA consortium expert in data analysis algorithm, and he will give us an overview on stochastic gravitational wave signals in the LISA band. So Nikos, please start sharing your screen and take away from here.
Thank you very much for the very nice introduction. Let me share my screen. I hope this will work. Does it work?
Yes, yes.
Okay. So let me put this here. Okay, so yeah, thank you very much for having me. This is a very nice opportunity to talk about stochastic gravitational wave signals. So this is meant to be a kind of a summary or an overview talk. So I'll try to summarize what we expect to see with LISA concerning stochastic gravitational wave signals. And as a disclaimer, there's a lot of work by many people on this. So if I forgot some kind of reference or point to some talk, I have to apologize in advance. So without further ado, let's start with mentioning why stochastic signals are important. So they are very important because they will, the signal itself, right? So they will give us a lot of information about underlying population models for the given type of source. And they're also important because they will challenge our data analysis efforts. They will contribute to the overall noise budget of the instrument. And there's going to be a lot of signal overlap, which will make everything a bit more challenging. That's why there is a lot of effort ongoing on developing this global fit algorithm that we discussed, that Tyson discussed in the beginning of this conference. And also, we know when we want to search signals from cosmological origin that are typically, they are lower signal to noise ratio, they will challenge their search as well. So I will make the summary of what we should expect for LISA, and also maybe some implications to data analysis, but I think this is a different monster to fight for another day. So I'm beginning with this plot. 90% of the presentations about LISA begin with this nice colorful plot because it's. But I think it's very nice because it shows all the types of sources that we expect with LISA. So we have the characteristic strain of the LISA, all the sensitivities across the frequency band. And the usual suspects are the massive black hole binaries. These are transient signals that appear with huge signal to noise ratio, or at least we expect them to appear. And then we have the compact galactic binaries in the vicinity of our own galaxy, and these are I don't know the color, something like magenta color. These are almost monochromatic, and we are going hopefully to disentangle a few thousands of them. Then we have the stellar origin black hole binaries. These are the LIGO-like sources that they are also monochromatic. They appear a little bit higher in the band, and we might potentially see some of them traveling to lower frequencies. And then we have the extreme mass ratio spirals that also appear everywhere in the band. So, in general, this is what we have, plus some possibility to detect cosmological signals. And what we can do is we can try to pick one of these type of sources one by one, and see what is the potential of creating a stochastic signal. So we can begin with the usual suspect again, which is the compact galactic binaries. We have seen this many times, and we have been discussing it within the LISA consortium and the collaboration forever. So This is the shaded gray area that we had in this plot before, because there's a lot of them and they are overlapping one with another, so it will be very hard to disentangle, dig in the noise and get more sources out. So the number of sources play is an important factor. If you have a big population and then if you have the signal overlap with the sources, then it really affects our data analysis capabilities. So these two factors are important of creating these stochastic signals. So if we want to study, all these type of sources and how they create stochastic signals, we have to examine both of these items above. Start from the population model and then do some data analysis and see what is remaining below, in essence. So exactly, this is the steps. We start with the given population models. We have to simulate all the waveforms in the LISA band, and for a given duration of the mission, and then we need to perform data analysis. I get all these resolved sources, and then in the end, after resolving what we can for the given duration, what remains would constitute the stochastic signal. So that's why, this is the global fit that was discussed in the first day by Tyson, Grinberg, and also yesterday evening in the data analysis session. Because we will have all these many types of sources, and we also don't know the number of them, we have to iterate all over the type of sources in some kind of this following this cartwheel scheme. We have, for example, when new data comes into ground, we have to analyze one type of sources. This is ultra-compact binaries, and then at the same time we update the model, the instrument model, the knowledge that we have about our instrument capabilities, and also after subtracting the best our best found sources, we can then pass the residuals around and start looking for another type of source. So this kind of cartwheel scheme is being followed now by many people. And this is what people do. I like to show this video because it shows what it has been happening to now. I'm guessing in the future many more types of solutions will come. For example, if we want to look for Gaussian pulses in the data, this is what happens here. We leave this transdimensional Markov chain Monte Carlo to explore a parameter space that changes in dimensionality. What you see here mu is the position of each of these pulses. So you see we are exploring a parameter space which is changing all the time. And then at the end of when the change converges, you have a marginal on the k, where k is the number of pulses in the data, and you will have a nice distribution of this as well. This is what we try to do. Many people try to do within the consortium to solve this global fit, but of course the problem has many orders of magnitude. It's many orders of magnitude more difficult because it's not two parameters like the mu and sigma here, but it's galactic binaries and mass black holes. Each of them have multiple parameters, and it's more difficult to get them out of the data. So this is a lot of effort ongoing, and but as you can imagine, because of this high dimensionality, and there was decades of effort to arrive to where we are now. It was shown in the beginning of this conference, but there's a lot of also tuning. If you want to have a global fit ready, you have to make develop the whole cartwheel, and also need to tune your MCMC running, and also it's quite computationally expensive. So it kind of forbids us to use this global fit to scheme to do this kind of estimation of first level estimation of the foreground or for background signals that we want to do here. So I'm just listing here the list of talks that I am aware of for discussing the global fit. All of them have already happened. It is very, very interesting. And there's a lot of data analysis methods for different types of sources in the DA sessions. This is also very interesting to follow. And I urge people to join to discover how challenging and nice is to work on this problem. So the first thing that we need to do is to simulate the data analysis of LISA, and we can do this by following a simplified approach. Right? We cannot do this cartwheel scheme again. So we can define an iterative process with loose criteria that help us classify if this source is detectable or not. And this, for example, could be an SNR limit. Right? We define an SNR threshold that we say this type of source is detectable if its SNR is above 20 or 50. And then if this happens, then we can say that it's detectable and we subtract it from the data. And then what we basically do is basically loop over a known catalog of sources, and we try to dig in the noise, compute scenarios iteratively each time. So this kind of method is generic because virtually we can apply it to any type of source. We have to be careful, because each source type of source has different waveforms and different complications. But most of the time it's idealized. You can try to make it more realistic, but it's idealized because there is we don't do this parameter estimation that I showed you in this toy example earlier. That we sample all parameters simultaneously, so there is no source overlap. When we subtract the source, we subtract it perfectly, so we leave behind perfect residuals, because sometimes when you find the source, there is a distribution of the parameters. So when you try to subtract it, you subtract a little bit of signal, or you leave a little bit, you subtract a little bit of noise, and then there is a lot of a little bit of signal being remaining there, which piles up as the more sources you try to subtract. And also sometimes, it's easier to assume that the noise is ideal. Nevertheless, it's a very useful tool, and I'm going to demonstrate how it works. This is the light gray is, for example, the compact galactic binaries dataset. The dark line is the solid line is the noise of the instrument. And the first thing that you do is you compute a first estimate of the foreground noise, which is shown with orange. And this is just, in this case, it's just a running median on the dataset. And then you loop over the catalog, you compute the scenarios, and you say if the scenario is higher than this threshold, I subtract it. And then this is what you end up after the first iteration. And then you do it again. And then you loop over the catalog, and then you go up until you have convergence. And after many iterations, you get to a point where you have some result which is stable. And this is magenta line is our final estimation of the stochastic signal. So this is useful because, as we said, it's fast and generic. We can combine multiple populations because you can get loop over multiple catalogs, right, for different types of sources. And of course, it's quite idealized, and it's using many simplifying assumptions. But in the end, what it gives you is like an estimate of the stochastic signal, and also you get signal to noise ratios for the resolvable sources, and also you can do some kind of semantic analysis with respect to the final stochastic signal. And of course, there has been a lot of improvements proposed, particularly for the compact galactic binaries, because when I showed you these plots earlier, I was just plotting 1 year of data, but we know that this confusion foreground is going to be cyclostationary. So when I was plotting the 1 year of data, I was kind of disregarding this kind of information that is also useful. Okay, so let's go to the first one, the compact galactic binaries. There is a lot of, there is a lot of talk in the astrophysics and the compact binaries session. A lot of very interesting stuff. There was a very, very nice overview talk by Sylvia Tunen on the first day. So I think a lot of these things have already been discussed a little bit. So I'm going to skip most of the details. And I'm going to try to focus on the actual data analysis implication, how the stochastic signal will look like. So depending on the population model, we expect to resolve like maybe tens of thousands of sources. And what will happen is that, once we begin operations, we will not resolve all of them at the same time. We will have to gather data. And the more data we gather, the more signal to noise ratio we accumulate, and we will better resolve the underlying sources. And that is what is shown in this plot here. I hope that this is my video is not blocking it. For example, if we start with half a year, you can see that the confusion signal is pretty high. But then as time passes and then we reach the 10 years margin or observation duration, we dig better than the noise, and then we manage to resolve more sources. So the confusion signal shrinks with time. Again, it's a cyclostationary, and this also complicates things in data analysis. We have to take into account when we try to resolve other sources. And it's one of the main reasons we need the global fit, because we have all these very numerous, a huge number of sources that we are going to resolve, and they have all this overlap with other sources. We can get a lot of information about the properties of a galaxy and its evolution history by also looking at the spectral shape, which is also dependent on the model. This is what I'm plotting here, taken from the thesis of Mary Gergusi, but the data were kindly provided to us by Sylvia Tunen and Valeria Korol. And you have, if you start with the different parameters for your population models, then this manifests, it will have a different kind of stochastic signal in the end in the LISA band. And this is something to keep in mind, so that we, unless we fly, we will not be exactly completely certain. We will not have very strong priors on this on the parameters of the model. And there is also a chance to get some information from extragalactic weather binaries, but I haven't included this in this discussion here. Okay, so you can also do quickly, I mean, with the result sources, what you can do a lot of things. So for example, you can devise the hierarchical variation model to get information about the population properties, because I'm writing this kind of model here. So for example, this is the likelihood depending on some parameters of the waveform theta, and then the prior on theta depends on some hyperparameters beta, because these are the hyperpriors, as we can call them, of the whole population, because each parameter theta is being drawn from this population prior. And what you can do is you can try to fit it together, when we get all the data out, and you can get all these nice PDFs for the different parameters of interest. For more, you can check the talk from Mary Yorgusi, who is going to talk about this. I mean, I think, yes, it's a pre-recorded talk, so you can find it if you need to check it for more details. And this has already been proposed in the context of LISA, of course, by Adams et al. In 2012, but there's been a lot of this kind of work for the LBK collaboration already. Again, I'm just listing a few talks that I found in the astrophysics and in the compact binary session. These are very, very interesting. So I guess all the details can be, a lot of details can be drawn from these talks. Now let's go to the second category, which is the stellar mass black holes. And well, the LBK collaboration has given us a plethora, a catalog of resources. So, but we can use them. It's a good starting point to start extrapolating from the LIGO band down to the LISA band. And what we can do is work in the same way as we work with the galactic binaries. We take a given population model, and then we estimate the confusion noise in LISA, given the assemblings that we get from the LBK collaboration. And then we can do also a forecast on the resolvable sources based on this information that we have. So Jesus Torrado is going to talk about this. This is a work effort by a lot of people, but Jesus is going to give a very good overview of how we do exactly all these things. I'm just going to present a few key points here. So there's two ways to get an estimate of the foreground signal. So we can do it analytically. If you follow if you start with the energy emitted by binaries emitting gravitational waves, and you can try to get an analytic formula for a spectrum of the omega gn or omega gw, which is the energy density, and this is how it looks like. So you have the prior on the chirp mass here, and you have the rate depending on z. And as you notice from this equation here is that you are ending up is that you have a power law model F2 that follows this shape, this F to the 2/3, and all the other population parameters are basically details that tune this amplitude. And this is something that we can use to extrapolate back to LISA analytically. But there is also, all right, so this is the recipes of how to do this exactly. You can find in these papers, but I'm sure there's more. So again, apologies if I forgot to add some things here. But there's also a way of how you can do it numerically. You can choose an observational time, right? Again, as the same thing that we did for galactic binaries, and then you can simulate catalogs based on the mass functions and all these details that you have for the population. And again, with all the uncertainties that come from the LBK results. You can use some waveforms to produce the data, and then you have to choose an SNR threshold to classify some of these sources as detectable, and following this iterative scheme that we followed before. And this is what we have. This is one of the results that we had. And on the left side, you see the stochastic signal that you would get with for the stellar origin black hole binaries. The red line denotes the theoretical prediction, and all the blue up to green is data. So rho 0 here is the SNR threshold chosen for classifying sources as resolvable. And as you can see, if we start with rho 0 equals to 8, we subtract a few sources. So I mean, very few of them in general. And then, the stochastic signal is not affected at all. But if you start lowering the threshold, naturally, we start digging in the noise in the same way as we were digging for the galactic binaries. And you can see that we can, there is this bend here on the high part of the spectrum. And this is the same figure. It just says zoom out to show where the compact galactic binaries are going to be, and also the noise of the instrument, just to put this signal into context. Now, I mean, we have already these estimates of stochastic signal, but now we can try to see how detectable this will be with LISA. I mean, this thing that we saw before, is it truly detectable with LISA? What will are the parameters, and how well we can determine if its existence? So assuming that there is nothing else there, just this stochastic signal, what we can do is we can get the posterior samples from the LVK analysis, and this is what they have for an amplitude of this signal at this pivot frequency, and this is what they have this histogram, for example, as the uncertainty for the amplitude given the observations that they have. And then what we can do is we can try to take different values. This is what these lines mark of this stochastic background, and try to see how well we can get the amplitude or some parameters of the two parameters, this amplitude and spectral tilt for this signal with LISA. And as you can see, starting with the lowest, let's say, with the lowest amplitude on this graph, which is the orange one, you can see that we can we say the data represent the error bars, right? So you can see that we can probably determine the shape of this spectrum pretty well. Again, disclaimer that this is we do not take into account any other signals present. And of course, as the signal gets stronger, we have better ability to get it out. And what about the detectable sources now? I mean, after we do this analysis, we get an estimate of the stochastic signal, but we also have some kind of we have an estimate of the number of detectable sources. And what we can do, again, Jesus is going to talk about this in detail. We can get a subset of the posterior samples from the LVK analysis, right? And then for each sample, we can estimate the stochastic signal that we get out of it, and also try to simulate a few sources that have a relatively high SNR, because if we try to do simulations with up to very large Zs, then we have millions of waveforms that we need to generate for each of those posterior samples, and this is quite an unfeasible computation, essentially. So but instead we can calculate only the high SNR ones that we can keep. We can try to calculate roughly the SNR of each of the sources, and then you keep only the ones that are above SNR2, the ones that are potentially detectable, let's say. And then you add them on top of the stochastic signal that you have estimated before. And then you can try to make a histogram of a prediction of the number of sources that we should expect for LISA. And this is what we did here. So the different colors mark the different SNR thresholds for detection. Red is for SNR above 8 are detectable, green with SNR 6 above 6, and then blue with SNR above 4. And as you can see, is that without being optimistic, we will kind of detect quite a bit of sources, and this is direct detection, right? And by being optimistic, we are drawn back to this red histogram, which is we would have a few detections or even none, and this is what we get from this result. I mean, it might be maybe pessimistic for somebody from this point of view, but this is remained to be seen when the mission flies. Again, this is work from by many people, and I think this is going to be divided into a couple of papers on discussing the stochastic signal on the result sources. There is on this note, there was a recent work by Tubiana et al. This paper just appeared in arXiv last week, which I think they took LVK events basically, and they tried to look at them in the LISA data, and they found that very few sources can be classified as detectable, and even less directly. And but also they try to also set a threshold, an SNR threshold for direct detection. So they set it. I mean, I think which was in agreement with 3 other studies in the past to 8 and 5 for archival searches. But if we see this, that if we take this threshold here as a confirmation, we are again confirming that we are on the lowest part of this histogram that we saw before. But if we do archival searches, I guess we will do a little bit better. And Alexandra, I think, is going to talk about this in one of the compact binary sessions. Now, for supermassive black holes, I mean, we can try to do again the same exercise and try to figure out if they will leave any kind of stochastic signal. I mean, because usually they are not the usual suspects, because usually they appear with very high SNR and they are relatively easier to be resolved sources. So what we can do is we can take the 3 different population synthesis models. This is called this POP3, Q3, Q3D, and Q3ND. And I'm adding all the details here, but I think that you can read more details in these papers here. And we can try to see which one of them would generate potentially stochastic signal. I mean, with all the implications. This is not exactly the same types of sources as before, because they are not monochromatic, right? And okay, so I forgot, this is work done by Daniele Langherudi in collaboration with Elena Maria Rossi. So I think this will appear soon in archive, I hope. So what we do is we choose an observational time. This time is 5 years, and I'll explain in a bit why we do that. We simulate catalogs using the Phenom HM waveforms again, and we analyze data from year 1 to year 4 because we want to have some continuity. Because we basically spread the time of coalescence uniformly in this observational time. And then again, we have to set an SNR threshold for the detectable sources and follow again this iterative scheme. Of course, there are sometimes very, very loud sources there, and if you try to plot the spectra, it will destroy everything. So you have to do some kind of pre-selection. So you subtract all sources that are above hundreds of SNR or 50 of SNR, and to allow for this procedure to continue. And then this is what we get. What you get for these 3 catalogs. I mean, this is just an iteration, right? This is I mean, a realization of these catalogs. And as you can see, for the 2 blue, the Q3 cases, they are very, very low. So they, I mean, these are probably residuals that do not really matter. But the POP3 population model can potentially give us some kind of stochastic signal, or not even stochastic, or some at least complications in the some addition in the overall noise budget that we might need to take into account. And in the end, what we did is we analyzed this data set we chopped the data set into 2-month segments, and we started seeing what's beneath. And what we saw is that there is always a little bit there was a lot of sub-threshold events. Basically, this is what happens. A lot of sources that are not detectable, very, very low SNR, and thus they are not subtracted, but still they are mostly look like a popcorn noise, like a popcorn noise translated into lower frequencies, and then you have this kind of fluctuations. And this is a zoom into the noise area of the like in the noise, and you can see how this fluctuates a bit. I mean, this is not much, but still it can be used to do to probe some properties of the underlying population, and maybe it's useful to signal, but it definitely could complicate our data analysis efforts on top of everything as well. Right, and then I'm going to move to embrys. So there was from previous works in the last years, there was some studies. The last one was from Panetti and Cesana 2020. And it was shown that for some population models, we would expect some type of stochastic signals from these type of sources because they are very long-lived. They spend a lot of cycles in the LISA band. And if you have many of them, then you will have all of them contributing at the same time, then you would get something that is unresolvable, a signal that is unresolvable. And what they did is they took all these types of models that they tried to model all these mass functions, models the spins, or the environment around these objects, and try to using the AK waveforms, if I remember correctly, try to model all these stochastic signals, how they will appear in the LISA band. And this is the result that they got there with this semi-analytic approach. So you see, even from this plot, that there is some possible stochastic signals from these objects. Federico Poggioli is going to talk about this new work that we try to do following exactly this iterative procedure and with updated waveforms, and see if these two type of analysis coincide. But this is what I'm going to spend one slide or two here, summarizing. And I will point you to his pre-recorded talk. He's doing a very good job in explaining everything in detail. We simulate, given all these populations, we simulate the waveforms using the AAK waveform, using the few packets that was written by Michael Katz, and it's publicly available, if I remember correctly. And then we simulated all of the catalogs, and there was some tweaks that we had to do, that Federico had to do to leave out very weak signals and also accelerate the procedure. So instead of, because simulating all these very many sources also was problematic, it takes a lot of time. And then we had to adopt an observation duration of 4 years, and again we have to assume an SNR threshold for all the sources that are detectable. So we set this SNR threshold to this 20 because of this the particularities of this type of source. And this is what we got, which is it's in different units than the previous plot, because this is TDI units, and if you put them side by side, I think they're quite comparable also on the number of sources that are classified as resolvable. So taking all these models, there's a great insanity on the underlying model, of course, but at least we get a good idea of how things work and what to expect for LISA, right? Again, finally, there is cosmological signals. There is a lot of. I will not spend time on this because I'm not an expert. So I will point to the LISA cosmology white paper. There is a lot of signals that we expect to see in the LISA band, a lot of models that would predict a signal in the LISA band. All of them, we don't really know the parameterization. They might be with high SNR or very low SNR, and so I will point people to the cosmology session and also to the cosmology white paper for a great summary of those signals. But they also, I'm showing this picture here because they shows some of its shape. Mostly, sometimes it's power law, sometimes it's has kind of Gaussian shape that it will appear distinctively into the LISA band. And what they try to do is, because of these different shapes that are competing, is that the cosmology working group has invested in developing algorithms to fit spectral shapes without prior knowledge on the underlying signal. And this is what they do: is they divide the frequency spectrum into different segments or bins, and then they fit individual power laws. And then if two power laws are too similar to each other, they use model selection techniques to join those. So this is kind of way of fitting signals that have different that they want to basically be model agnostic, right? So this is one of the solutions that it was proposed. So how it will look like if we fitting everything together. I hope I'm still within time margin. I still have a few slides. This is how it looks like. If you what we discussed today, we have the different stochastic signals. The first one is to repeat, is non-stationary, or cyclostationary. It's anisotropic because all this signal is produced mostly by the galactic disk, dominating after subtracting all the bright sources the spectrum below 3 millihertz, and it has this particular shape that depends also on the will depend. We will figure out when LISA flies. Then we have the massive black hole binaries, which is a kind of non-stationary popcorn noise, and its existence needs to be proven because we only found this kind of underlying noise for the POP3 model. And then we have the stellar mass black hole binaries, which is stationary, isotropic, but we have a good prior on the amplitude and spectral shape from the LIGO collaboration. And of course, as time passes, there's going to be more measurements, and we'll have even better idea about the signal. And finally, we have the Embry stochastic signal. There's a lot of unknowns. I'm just plotting here for the sake of adding everything together. The most optimistic model, optimistic because it's higher SNR, but optimistic because it will complicate data analysis for the rest of the signals because it's quite high. And on top of those, we will have to not forget that we will have all these instrumental noise properties, right? So there's a stochastic signal, and also we have, glitches, gaps, and slow variations of the noise. Our instrument will be breathing, and all these kind of things that complicate the global fit even further. So we need to, to get down to those signals, we need to assess our knowledge on the spectral shape of the noise, and also to know the overall budget of the instrument with very good. Of course, the better you know the instrument, the better the results that you get in the end. And because I spent way too much time to making this very silly cartoon, I'll have to play it for you. It's just adding everything together. After 4 years of observations, it's a cartoon again, so everything is kind of exaggerated. I hope that you can see it. After 4 years of observations, this is what will happen. You have everything. You have this popcorn noise from the supermassive black hole binaries and the compact galactic binaries going up and down due to the antenna pointing of LISA. And with this, I can leave you having these points. So, okay, so the first, all this work is assuming independent analysis for all types of sources. In the future, we can combine all of them and get an overall stochastic signal for the different models. And this will be more realistic, but this is just one by one. And but LISA is going to measure a huge number of signals. We get a lot of different types of sources. There are potential for different stochastic components, right? We don't know if all of these colorful lines will be there. And we will have, this will bring implications to our data analysis effort. But I think we have a lot of advantages. There is a lot of very nice talks that we had up to this point. And we will hear more about using new channels, new global fit algorithms, noise modeling techniques, and all these nice things. And with this, I will stop, and I'll be happy to take any questions.
Thank you, Nikos, for a very extensive summary. I think you covered all, or most of it. So let's now take the questions. I invite everybody to submit them via Q&A box, or you can also raise your hand and we will unmute you. So while we're waiting for the questions, I have a few from the panelists here. So the first one is why the massive black hole binary background is a popcorn like noise in the data.
So because, okay, so the SNR for these sources, I mean, there are people that know this much better than me, so they can comment as well. It accumulates fast during the last days of the weeks or before merger. And what you have is a lot of successful events. What you have is these small blips, this is still not enough to be detected, but still you will see it in the noise. And if you have a lot of them during this time of where you compute your PSD, they will appear as a kind of raise in the noise.
And I'm guessing it is very uncertain how many of this.
Right, it's model dependent, and it's it has a center as uncertain as the model that we have for them.
Okay. So the next question is, could you explain the TDI plot for the MRIs, which was 1/Hertz unit and the magnitude of 10 to the minus 42?
Yeah, this is TDI units. I mean, this is not this is not deconvolved by the sky average response of the instrument. That's why it has this shape. Otherwise, if I was doing that, it will have this usual kind of shape. So it's just the output of TDIX channel, for example, that we have one of them.
So I hope that answered the question. And let me, as we are running out of time, let me ask one more for myself. So you mentioned that in the future you plan to combine all of this together, and I'm wondering what challenges do you expect there, and how, you know.
I mean, this is because, you know, it's not real. It's again simulation of data analysis, because you're using only this simple SNR criteria. So the challenging is, of course, you know, is simulating all the catalogs and adding them together. It takes a little bit of time, but also you have to mention all the caveats that do this. The code is there. I mean, the code that we have can handle it. It can handle many catalogs and many types of sources, but you have to take care, for example, subtracting very bright sources beforehand for each of the catalogs that we have. Very small practical, you know, issues, but also we need to always remind that this is not real data analysis, right? It's just trying to estimate everything together. Practically, there is not a big challenge, but you know, at the end we have to mention all the caveats of this method.
So I see one new question popped in the Q&A. Would it be okay if I leave you, Nikos, to answer in a written way, and we switch on to the next talk, because we don't want to be late. Thank you again for a nice summary.
Thank you very much for having me.
And now let's welcome Martina Muratore from the University of Trento. She's one of the co-chairs of the LISA Early Career Scientist Group, and she will give us an overview of the group activities. So welcome, and the floor is yours.
Hello to everyone. First of all, thank you for the organizer to let us present our activity. I will share the screen. Okay. Do you see the screen? I hope so. Okay. Yeah. In case interrupt me. So first of all, I'm going to present the activity that we have been doing this year, and in general to give an overview of the LISA Early Career Scientists, that is also known as LEX. So as Valeria said, I'm one of the chair, and so I'm presenting also on behalf of Elisa Maggi and Michael Katz, that are the other new two chair of the group. So just a bit of background. So the LEX was founded around 3 years ago, and is open to the so-called early career scientists. So for early career scientists, we mean that it's not a straight, let's say, age from joining the group, but in general is the group is good for people that are doing the PhD, the postdoc, or just got early position for like professorship. So it's really open to everyone that feel to be an early career. The group is growing every day. So at the moment we are 237 members. And for the idea why this group was founded. So here I reported just a brief and quick reason why we decided to found the LEX group. So first of all, we saw around the early career people that actually there was a need to discuss the value shared by young generations. Also, the idea of the group was very important in order to support career development, job, and also grant opportunity. We saw also that the group was actually useful in order to foster collaboration between researchers working in different environments and also in different groups. And last but not least, the LEX has the goal also to promote participation of young scientists in activities like leadership, outreach, also diversity, and also to lay the foundation for a functional, enjoyable, and really all-inclusive environment. So the idea of the LEX is that, we've been changing a bit our organization. So compared to the previous 2 years, so at the moment the LEX chair run the group for 2 years. At the beginning was just for 1 year, and any chair can at maximum have 2 mandates. So for example, for my case, that was a chair 2 times. I cannot candidate myself another time. And regarding how we decide who is going to be the chair, we actually done election, and the elections are done online and are open to all LEX members. And we also apply diversity rules. So, for example, we are 3 chairs, and every time we want one PhD among the chair. We also consider the gender, if there are female, if there are male, for example. And so we try to be as much variety as possible. So regarding what kind of activities we have been done during this year. So first of all, we are trying to adapt a little bit our LEX call, considering the interest among our current attendees. So in particular, we were doing the meeting, two meetings a month. At the moment, sometimes we do 1 meeting or 2 meetings, depending what we have to discuss, depending also what kind of topic people want to hear. So for this reason, we also have conducting surveys to ask what kind of activity you would like that we organize. Well, in this umbrella, there are the software series and cross-disciplinary talks that we have been running these years. And the idea of cross-disciplinary talks, for example, is also to invite young research, like also PhD, if they want to try their PhD defense talk before actually the day. So in this case, any young people that would like to try any kind of live talks, also PhD, can ask to give a talk. A very important activity that we are doing are the mentorship program, and I'm going to speak more in detail later, as well as the so-called GWX. And the GWX is another activity that I'm also going to explain later. But just to a summary, the idea of the GWX is that we are trying to build a group where different people coming from LIGO, Virgo, PTA can be involved. And so in this way, all the general activities like media outreach, career opportunity, or well-being and mental health are actually organized inside the umbrella of this GWX. Other activity that we have been doing during the year is the participation of LEX in data policy. And also we have also trying to spread out all the information that are actually sometimes difficult to reach for people that doesn't belong to all the working group among LEX. So what we have been doing was to do quarterly updates from chair from different working groups. So we asked them to attend our LEX call, and in this way, also people that doesn't belong in all working groups can actually have an idea of what was going on and also ask questions. So regarding actually what we would like to do for the next year. So first of all, we would like to keep running our LEX mentorship program. Indeed, all of you should have received an emails regarding a new call for mentors and mentees. There is also the usual job fair that will happen in fall. And we also would like to do with LISA what actually has been done already in LIGO, the mental survey. So in LIGO, they organize a survey from psychologists among early career scientists, and actually it has received very good review. So we would like to do the same in LISA, also maybe in the umbrella of the GWX activity that I described before. And just if you would like to, there is also another activity that we are building together with the LISA social team, LISA media social team. And if you would like to actually join the team, I reported the email, so you can just directly contact them, ask them for more details. And in general, we are trying to organize many activities, lectures, and also scientific events in order to help the LEX to follow the evolution of LISA, in particular for the LISA adoptions. So just to introduce the mentorship program. So we are, as you see from the email, we are actually looking for a senior consortium member and also junior postdoctoral researcher. For junior postdoctoral, we mean someone that has got the PhD around 1 year ago. And we ask for volunteers, and also in case if you want, you can also nominate someone else in order to be a mentors. And if you actually would like to nominate yourself or someone else, you can just go to this form. Actually, you will find all the information. The same applies to mentees. We also encourage who would like to be part as a mentee of the program to actually use this form. So I would like also to underline that also the senior, meaning the professor, can actually invite their student to join this mentorship program. So in order, if you want to be a mentee can be like bachelor, master, PhD student, postdoc. So everyone really can participate. I also would like to underline that you can also be a mentor and a mentee at the same times. so there is no problem for that. And the deadline for apply is the 9th of September. How actually we match our mentees and mentors. We asked the mentees to fill some questions, and actually, so they also rank the mentors, giving a score from 0 to 10 regarding how much they will be interested in what the different mentors would like to discuss. And our algorithm is going then to run from and consider different answers from different mentees. And so in this way, it is really everything automized, so there is no bias from us to choose and to choose the couples. So the mentors program will start on September, and we will have a kickoff meeting at the end of September. And after that, we encourage mentees and mentors to actually organize their meetings by themselves. And for a rule of thumb is going to be around 6 months. So regarding the GWX, so the GWX is a new organization, and the idea of the GWX is actually to design and unite all the different community among the early career scientists, as I said before, like among PTA, LIGO, and actually the scope of this new group that we form is actually to address the needs of early career scientists, and so to foster a healthy professional environment, and also share career opportunity, also learn professional skills. So if you actually would like to be part of this GWX, like you really would like to start organizing activity, also to be really active part of the group, you can just contact the email that I put here. Or if you just would like to receive news and know what's going on, you can just subscribe to this mailing list. And here I finish my presentation, mostly giving you some useful links. So the first, these links that you find here are two spreadsheets about the host institute that host like scholarship. So if you get a scholarship and you would like to do your work somewhere, you can just look here, and here we report all the host institute, as well as in the other fact sheet. We have a spreadsheet. We actually report the kind of fellowship that we have, that we are known on, for LISA, for LIGO, and for other mission. So these two spreadsheets are in general. We sent around from the LISA consortium, and so people can professor that want to advertise any of the position can just leave the contact there, so we can share among LEX. So also to underline that there is a LEX wiki that is finally working, and all our activities, all our telecon and everything is really here, so you can find everything here, as well as information regarding the mentorship program, the GWX. We also have dedicated website for this. So for the mentorship program is the following, and for the WEX is the other one. And with this, really, I would like to thank you, and also to say that if there is anyone in the call that is not part of the LEX and would like to join, please really just email us. And thank you.
Thank you, Martina. And thank you for running all these activities for other early career scientists. I think
it's not me. It's really Lisa is doing lots of work, and also Michael.
To everyone,
all the LEX, all the early career science, we work together, as you know.
So thanks to everybody who are contributing to this. So let's see if there are any questions. You can submit them via both chat or the Q&A. And while we waiting a little bit, I think that it is worth to mention as well that LEX is open also to more senior scientists to support early career scientists, right? And we used to receive a lot of messages, suggestions, and well, any useful information from them. So if you would like, you can also be a supporter of LEX, right? So I don't see any question. I guess you're very clear and detailed.
People are tired. They want to eat.
Yes, and it's also lunchtime. So I would like to thank you again. And also, let's thank all the speakers of this Wednesday plenary session. All the talk were extremely interesting, and you can continue enjoying it on YouTube. They will be available hopefully forever for you. I would also like to thank all the support team from Glasgow who are running all this behind the scenes. So you sort of seen Alasdair, there is Andrew, David, Harry, Rona, Michael, who are helping to make this consortium happen. So thanks to everybody, thanks for listening, and let's take a break before the afternoon, and I leave the floor to Alasdair if there are any updates. No, it's fine. I think that I can tell from the program, right, we restart at 3 p.m. Central European Time with parallel sessions. And if there are any...
Alasdair's mic seems to not be working, but thank you very much for hosting, Valeria, and we will see you all in the afternoon.
Yeah. See you then. Bye-bye.
Thank you. Bye.